Trigonometric ratios. Fill in the fundamental trigonometric ratios below. Sine, cosine, and tangent. The name of the angle follows the trigonometric function. If the angle is named alpha, the function values become sine alpha, cosine alpha, tan alpha. Alpha plus beta here equals 90 degrees. If the angle is named beta, so this is the one we're talking about now, the function values become sine beta, cosine beta, and tangent beta. If you are given the lengths of 2 or 3 sides of a right triangle, the trigonometric ratios let you find the measures of the acute angles. If you are given one side and an acute angle, trigonometric ratios let you know the lengths of the unknown sides. We expand our definitions to right triangles of any size by noting that the ratio of sides of similar triangles are equal. So here, we can slide this over, and you can see that these two triangles are similar. The opposite side to the adjacent side to the hypotenuse is an equal ratio to sine alpha, cosine alpha, and 1. It follows then that opposite over hypotenuse equals sine alpha over 1 equals sine alpha, and adjacent over hypotenuse equals cosine alpha over 1 equals cosine alpha. There are two acute angles in a right triangle. Let's focus our attention on angle beta. So here we have angle beta up here, and we slide this triangle up to confirm that these triangles are similar. They both have angle beta here. And in these diagrams, the names opposite side and adjacent side are named with respect to beta. So you see this side here is adjacent to beta, and this side here is opposite to beta. So the ratio here, opposite to adjacent to hypotenuse, equals sine beta to cosine beta to 1. It follows that the opposite over hypotenuse equals sine beta over 1 equals sine beta, and adjacent over hypotenuse equals cosine beta over 1, which equals cosine beta. Note that the ratios can be simplified. So here we have sine theta over 1 equals sine theta, cosine theta over 1 equals cosine theta, sine theta over cosine theta equals tan theta. Here we have sine theta over 1 equals opposite side over the hypotenuse, which equals opposite over hypotenuse. Cosine theta over 1 equals adjacent side over hypotenuse, which equals adjacent over hypotenuse. And sine theta over cosine theta equals opposite side over adjacent side, opposite over adjacent. Alright, so here's a little cheat sheet. We have sine theta, which is, here's theta. Sine theta is going to be our opposite side over the hypotenuse. Opposite over hypotenuse. Cosine theta, here I'll color coordinate. Cosine theta is going to be adjacent over hypotenuse. And tan theta is going to be opposite side over adjacent side. These trig ratios are used so often that they are memorized by the expression SOHCAHTOA. So, S-O-H, which stands for sine opposite hypotenuse, ka, because that is cosine adjacent hypotenuse, and toa, tangent is opposite over adjacent. If you get confused by the vowel sounds in SOHCAHTOA, you could also try the mnemonic device below. Some old horse caught another horse taking oats away. Let's find the length of side x. The side that we're looking for is opposite the given angle, and the given length is the hypotenuse. We'll use the trig function that relates these three values. In this case, that's sine theta. This is the angle we want here. And we have opposite and hypotenuse, and as we know, because of SOHCAHTOA, sine opposite hypotenuse, so we have sine theta equals opposite over hypotenuse, and that is how we will solve for x. Alright, since we know that sine theta equals opposite over hypotenuse, and we're looking for opposite, here x is the opposite side from the angle, so we solve this equation for opposite, so which means that we multiply both sides by the hypotenuse, bringing the hypotenuse over to this side here, like that. So we have opposite equals hypotenuse times sine theta. Then we plug in the information we have. So our hypotenuse is 7.0, and we know that our angle here is 30 degrees, so we put in 30. We put that in our calculator and we find that sine of 30 degrees is 0.5, multiply that by 7, and we get x equals 3.5. Now let's find the length of side x in this case. The side that we're looking for is adjacent to the given angle, and the given length is the hypotenuse. We'll use the trig function that relates these three values. That would be cosine. Using our mnemonic device, SOHCAHTOA, we know that CAH, the middle part, is cosine equals adjacent over hypotenuse. And that is what we have here, the adjacent side and the hypotenuse. So we will use cosine theta. All right, we have cosine theta equals adjacent over hypotenuse. What we're solving for is x, which is the adjacent side. So we're going to solve this equation for this part here, adjacent. So we'll multiply both sides by hypotenuse. We get adjacent equals hypotenuse times cosine theta. So let's plug in our numbers. The hypotenuse is 9.0, and the angle here is 25 degrees, so we'll plug in 25 degrees for theta. We use a calculator, we see that cosine 25 degrees is 0.91, multiply that by 9.0, and we get x equals 8.2. Now let's find the length of side x in this case. The side that we're looking for is opposite the given angle, and the given length is adjacent the given angle. We'll use the trig function that relates these three values. All right, so when we're dealing with opposite and adjacent, that's tan. Using our mnemonic device, SOHCAHTOA, we can use the TOA portion, which is tangent is opposite over adjacent. All right, so we have the ratio here, tan theta equals opposite over adjacent. And in this case, we are looking for the opposite side, that is x. So we'll solve this for opposite, multiply both sides of the equation by adjacent, cancels out on this side, it moves to the other side. We have opposite equals adjacent times tan theta. We'll input the data that we do have, so we know that this length here, the adjacent length, is 9.0, so we'll replace adjacent with 9.0, and we know the angle is 50 degrees, so we'll put that in for theta. Use a calculator, we see that tangent of 50 degrees is 1.2, multiply that by 9.0, and we get x equals 10.8. Sine and cosine have complementary angles. The acute angles of right triangles are complementary. This plays out in some interesting ways. So we know we have alpha and beta here, and we have a right angle. Therefore, alpha plus beta equals 90 degrees. So if we solve this for beta, we get angle beta here equals 90 minus alpha, because we just move this alpha to the other side. And down here we have alpha equals 90 degrees minus beta. But visually, look what we can confirm. Sine of alpha, so sine of this angle, would be a over c. The cosine of beta would be a over c. So we have the sine of alpha equals the cosine of beta. So that's how this relationship between these complementary angles is interesting.